Okay, so we're going to start with this small capacitor. This capacitor is 0.1 microfarad. Okay, and then the capacitor that's also in here, even though this is bigger, it's not bigger capacitance. It's counterintuitive. So this is 0.1 microfarad, and this is 0.01 microfarad. So this one is 10 times smaller than this one. So when we plug in this one, we should expect a long discharge time. And when we plug in this one, we should expect a smaller discharge time. So 0.1, 0.01. So we're going to plug this into the circuit. Don't look at my poor circuiting habits. This should be in the 0 position before I put this in here. So I'll pop that in. I come up to my code where I have everything written out, right? So here's my code. Then I'm gonna push the reset button to run the code. So this is the 0.1 microfarads. That says 653. Now I'm interested in repeatability. Is it gonna be 653 every time I run this code? So I push reset again. Oh, 654, that's different. Hit it again, 653. 654, 653, 653. So this should show you, and you should always test the repeatability of your circuits, that it's going to be somewhere around 653. So I will look for, if I'm writing a code, my expected values, I would say is somewhere between 650 and then 670. Or if you want a tighter range, you can say 652 to 655, right? Because you always want to check the repeatability. So that's with the big microcontroller. Now, excuse me, that's with the big capacitor. Now I'm going to take a capacitor, take one that is 10 times smaller. So this is 0.01 microfarads. And then, so should this be at least 10 times smaller? So we plug that in here. So this is 10 times smaller. So will the new number be a 10 times smaller number? Well, the new number was 1/10 of this number is 65. So when I push reset, I expect I should get 65. I hit reset, I get 61. So that's approximately a 10th, right? So there you go. And just like with the resistors, I'm quite sure there's some variance in the production of these. That's why we didn't get perfectly a 1/10 of that, and that makes sense. This capacitor is 10 times smaller than this capacitor, right? So we have these capacitors. They're great big giant swimming pools. They like to fill up fast, and they like to empty fast. The bigger the capacitor, the more water you can have in your swimming pool. And what controls the discharge rate? The resistor. Now let's do this. Let's put in a smaller resistor. This resistor is brown, black, orange. So that's 10,000. Let's grab a resistor, maybe, let's do 1,000. Let's try this one, brown, black, red. So I'm going to pull this resistor out. And so because this resistor is smaller, it's 10 times smaller. When I run this code, now I reduce my R in this equation by 10. Right? So my time should also reduce by 10. So now I'm looking for a time of about 6, if my math is right. So I hit my reset button, boom, I got 4. 4 is roughly 6. Because remember, with this resistor, what's built into it is plus or minus 5% variance. So it can be as much as, the nominal value is 1,000. But then it can also be 1,050, or it can be 1,000 minus 5%, right? Let's check the repeatability, and it seems to be 4 all the time. So that makes sense. The smaller the resistor, the wider that valve is, and the faster my pool empties out. And so we just saw that. And also we saw that we created a mathematical model, and that mathematical model we backed up with a physical experiment. Okay, cool. So how can I use this in robotics? What's the point of all this? Now we're going to build a robot, and we're going to introduce another type of thing. So we're going to take away this resistor, think of this as the drain on the pool. The smaller the value, the resistor you have, the more it lets water go out of the pool super easily. And I'm going to replace that with a new electrical component. I'm just over here looking for it, called a photo transistor. So we're going to pull up a photo transistor and we're going to go over that next.